All right, welcome everyone to another OCP TAP call. This is call number 122. Today we have a summary of the Global Summit Roundtable by Rodney Cummings, and a little bit about Rodney. Rodney, during an over 35 years career at National Instruments and Keysight, worked on launch products, families for testing of network protocols. These testing products have addressed all industries and application, but Rodney's focus has been mainly on time synchronization and determinism and management. He's the vice chair of IEEE 1588 working group, and he has worked on a variety of standards in IEEE 802.1, IETF, ITU-T, and ORAN. His role as a timing architect at Keysight focuses on products for testing of time sync performance. He received his bachelor degree in computer science from University of Texas, Austin in 1990. So with no further ado, Rodney, the floor is yours.
All right. Thank you very much. Let me share my screen. And I'll pop up these slides. Let's see. I guess I can go into presentation mode, make it a little bigger. Here we go. Okay, so I can only see the slides at the moment. So to start off, this is kind of a disclaimer slide. So technically speaking, this OCP TAP call is jointly held with the IEEE Industry Connection on Timing in Data Centers. And when you joined the call, it mentioned a joint organizer. So in the context of this call, that's IEEE. So the IEEE legal staff and so on asked to post their policies and procedures, just like OCP, so that everybody knows what the IEEE procedures are in addition to the OCP policies and so on. And these are the links to the various IEEE policies on privacy and events like this one, so on and so forth.
Rodney, one thing.
Oh, sure.
Maybe you can flip the screen because you are seeing only the slides, but we're seeing the
the whole thing.
What you are supposed to see.
Yeah, I hate that PowerPoint does that. Yeah, thanks for telling me that.
You're welcome.
And of course, it's transcribing everything I'm saying. Let me try.
Oh, fuck.
Just press.
Maybe I'll just do it in this mode. Yeah.
Just press again, presenter.
Like this one?
Uh-huh. See what that does. Okay, so what you need to do is go back to share screen, like stop sharing, and then choose this other screen.
Yeah, good idea.
It actually opens up a whole other window, and you're on 2 instead of 3 kind of thing.
Yeah. Gotcha. So yeah, if I share again and just tell it PowerPoint, and now, oh, no. Does that look better?
Yes.
Yeah, that's it.
Excellent.
Okay, great. Awesome. Thanks, guys.
You're welcome.
So yeah, well.
It flipped again.
Oh, did it?
What happened? Yeah. Display settings, see in the display
Yeah,
settings?
you might want to stop sharing and then reshare. Yeah, and then reshare that specific window. Or yeah.
Gotcha. Yeah, now it's in a weird mode now.
Yeah, PowerPoint is not my friend.
It's not that, yeah. So that one.
Yes.
Fantastic.
There we go. Okay, and now I've got the split screen on my notebook, but the big screen,
yes.
What y'all see has the.
Yes.
And now
Perfect.
let's see if navigation oh, okay. Now I see. I navigate down here. All right. So there's a little disclaimer. So the actual presentation, I'll get to that. So this is a summary of the TAP roundtable discussion that we had at the OCP Global Summit 2024. So I'll kind of explain that. Kind of this slide. So the OCP Global Summit 2024 was in San Jose in October. I should have mentioned that. This was a really big event, over 7,000 attendees. It was my first time actually attending, but it was really informative for me. There were great demos in the TAP section of the Innovation Village. Lots of great demos of TimeSync being used there. There was a track of presentations at the summit. And that's a link to the slides and video for the various presentations there. And there were great presentations on timing at the Global Summit. But what this presentation is going through is at the end of the TAP track, we scheduled a roundtable discussion, basically just an open-ended discussion around tables. There were about 25 timing experts from various companies, maybe a little more. Open and honest discussion, but it wasn't recorded, like many of the other things are, thankfully, at OCP. And the reason why is that it was just intended to just be an open discussion. You know, there wasn't really a presentation or necessarily anything like that. But there seemed to be some strong consensus on important points. Like we did actually have a pretty good discussion, I would say overall. It was very active and very energetic and stuff. And so what I offered to try to do was to try to summarize what happened at the roundtable with some slides. So to let everybody know, just as a little bit of warning, I didn't take notes when I was at the meeting. So these slides are actually pretty much based on my memory of what happened and everything. I kind of regret that. In hindsight, maybe I should have taken some notes or something. So I may be getting something wrong, you know, in trying to kind of capture this stuff. So what I'm going to do is kind of go through the slides, kind of go through what I was summarizing and everything. It's only a handful of slides. And then after I kind of go through things, we can have a discussion. And as part of that discussion, feel free to correct me if I got something wrong or add something or bring up a new topic, whatever comes up. So that's kind of the intention here. All right. So to start off, Dan Biederman, who unfortunately couldn't make it today, started off the whole roundtable by showing a list of potential projects that students could work on as part of TAP's Time Synchronization Industry Academia workstream that he and Hesham chair, TSIAW. And there was a long list of projects, and they were really great projects, but you know, it was a relatively long list. And so, you know, the topic that kind of Dan threw out as sort of a starter topic was, hey, maybe we can look at this, and are there any particular projects that we could focus on? And so I think it was me that started out the trouble, I guess you could say, in that I kind of mentioned that, you know, like I said, it was the first time I had ever attended the Global Summit. And the Global Summit, for those that don't know, obviously focuses mostly on data center. It covers other topics, you know, for sure, but it is mostly a data center conference and event and exhibits and stuff. And as everybody knows, the hot topic among data centers is AI workloads and things like that. So a lot of the overall global summit focused on AI workloads in data centers, I would say. At least that was my impression. For example, the keynotes, like I listed here, were from hyperscalers and semiconductor companies, mostly talking about that. And a lot of the presentations that were in all the other tracks, you know, outside of TAP, many of them were focusing on challenges and issues with AI and doing large scale AI workloads and things like that. And the thing that I kind of noted when I was watching all these other presentations was there wasn't really much mention of TAP or for that matter, really using precise time sync or using PTP or anything like that. It seemed to be kind of absent. And so a question that I kind of asked was, well, you know, since we're here at the Global Summit, should we kind of take a look at these projects and focus more on AI as a topic for us to do projects and do stuff on. And that elicited a lot of discussion. Really, I would say really constructive, good discussion. So in this next slide, I kind of focus on that. So in this slide, I'm not necessarily trying to be comprehensive or correct in listing all the different types of data centers, or in listing all of the different kinds of applications that go on in the data centers. I'm just kind of pointing out that in the kind of threads of discussion that we seem to have at the roundtable, it seemed to kind of focus more on that orange arrow there, basically talking about a hyperscale data center, very large scale data center, and running AI workloads in that data center. Obviously, HPC and a lot of other applications are relevant, and time synchronization is actually used for many of those other applications, including distributed databases and other things. But it seemed like a lot of the kind of discussion at the roundtable was more focused on the AI topic. So I'm just kind of presenting this just to clarify that I'm not saying that the only thing that matters is AI in a hyperscale data center. Telecom matters, high frequency trading matters. All these other things definitely matter, and definitely use time sync. It's just most of the discussion that I'm talking about was really more around the AI topic, just because that was the topic of the day, because that's the event we were in. So with that, what I did here was I tried to take some quotes from various folks that were there, and I did check these quotes with the folks that I'm quoting. And so I'm going to go ahead and just kind of read these off. This was just sort of my attempt to kind of try to capture the tone of the discussion that we had and everything. So Ahmad kind of mentioned that in Meta's case, precise time, meaning PTP, SPTP, PTM, all these things, as many of us know, it's deployed, it's there, but many of Meta's applications are not necessarily using it. So in other words, the time sync in many cases, and I think that applies to other data centers as well, that the technology, how do we deploy precise time sync in a data center, that not that it's been 100% solved, there's still plenty of good work to do, but that's kind of been done. And we sort of know how to do it, and to get it there. It seems like the challenge now is that, well, for example, the AI workloads are not necessarily using that time in their flow of information to and from GPUs, CPUs, you name it. So I think Ahmad, and correct me if I'm wrong, he kind of phrased it as, we focused a lot on the how, meaning how do we get synchronized time and how do we do PTP and all these things, maybe not enough on the why, meaning in other words, now you've got it, well, how do you use it? And that seemed to be kind of a tone from a lot of the other comments too that were made. A lot from NVIDIA pointed out that around cloud service providers and AI, the value in the theory is promising, meaning the value of using synchronized time. However, the ROI isn't there yet. It's better if we apply to focus on a killer app and the ROI. So again, kind of echoing some of what Ahmad said as well, that it seems like now we need to kind of transition more to demonstrating the value, of synchronized time. Someone that I couldn't remember, maybe it was me, I don't know who, mentioned a phrase, over marketing is detrimental. And I remember a bunch of us, including me, kind of latched onto that and said, yeah, I agree. But to be clear, the little thing, the parenthetical expression that I have there was me, in that my interpretation of what that meant, it sounds a little negative. But what we really mean by that is, I think, is that there's been a lot of presentations from people that work at hyperscalers and people that work at semiconductor companies and so on, describing how, for example, precise time sync could benefit AI, just to use that as the topic at hand. But a lot of those presentations are, I think this is valuable and it would help and so on. In other words, they're not necessarily trying to say, it's deployed and it's running and 100% of the AI workloads are using it, right? But I think a lot of the people that view those presentations assume that. They assume that, well, I'm looking at a presentation by someone that works at so-and-so company, so that must mean that they're saying that it's done, it's successful, it's being used today. And that's what sort of we meant by the detrimental thing. In other words, people can misinterpret that. It's great to have an idea. That's how new ideas become successful. You evangelize them, you advocate for them. But sometimes people can misinterpret an idea to be it's being done today. And that confusion is, well, creating confusion, you know, and we need to be a little clearer on that. Kevin Stanton, many of us know, previously worked at Intel. With regard to a discussion thread we were having about silicon, like PCIe, PTM, and so on, Kevin mentioned that it's not about the direct cost, meaning area on the silicon die. It's often about the opportunity cost, where limited design and validation resources could be applied to reduce the risk on more mainstream chip features. So in other words, you know, there is a little bit of a challenge sometime in getting time synchronization into these chips, just because of ROI and opportunity cost concerns. Again, totally valid. A lot of us head nodded on those sorts of things. And then Med and I mainly Med, I don't know if I voiced it too, pointed out that the protocols for congestion that have been used in data centers for many years, you know, at least 20 years, maybe 30 years, I don't know, haven't used time really to kind of organize the traffic and so on. In other words, they've been, here's a burst of packets. I need those packets to go from A to B as fast as possible. Do it now. And they haven't really kind of scheduled things in the sense of using, say, PTP time or anything like that. Other applications in other industries have kind of sometimes gone down that road. But we just kind of pointed out, well, there's a mindset there, meaning, in other words, people have done it that way for decades, and it's sometimes hard to change a mindset. And so to the extent of trying to do things like that, there's just sort of a cultural hurdle to jump. And that makes things difficult. So it's, you know, in addition to the silicon concerns, there's just simply the, you know, the people that are running these AI workloads are just not used to thinking about using time to do that. And that's a little bit of a challenge. So that's kind of the sort of the tone of the discussion that we had. But in terms of moving forward, at least the way I looked at it, and I think a lot of us looked at it too, is we didn't really have many people in the round table saying, well, we should give up, or this is not a good idea, or, you know, anything like that. It was really more, you know, to say the glass half full, you know, it's not really a negative thing. It's just really more like, well, we need to maybe change our focus. Like Ahmad said, not as much on the how, but more on the why. And many of us still feel in the room that there's a benefit for AI to trying to use precise time, and that people are pretty open-minded. It's just we need to make things pretty clear, you know, to them in terms of the benefit and so on. So the idea was, and I think maybe even Dan said some of this too, that we need to produce data for the people that make decisions on the AI workloads, like how do those work through the data center and so on. Maybe not so much like as many slides with abstract concepts of, hey, you could do this and so on, but something that's more like projects with actual code and actual emulations or simulations that show it, that actually show here's you not using precise time, and here's you using precise time, and here's the benefit. We didn't really talk all that much about the specifics of that. Really, it was more just kind of, that's the area that we need to focus on, is getting more real and deeper into the AI challenges and protocols and code and so on. And it's okay for folks to make a statement like hyperscale data centers are using precise time for AI. I at least me personally, I wouldn't criticize anybody for having a presentation saying that or anything like that. It's a great thing to advocate. But again, when we see things like that, we need to dig deeper with questions like, well, at what stage is that? Is it just an idea you have, or is it deployed? If it is deployed, how many AI workloads are using it? How are they using it? Are they using it in the communication protocol, like maybe Rocky V2? Is it above the RDMA layer? Where is time used? Do you have open source for it? Because if you have open source, that's great. I could try it and I could see for myself what the benefits are and so on. And if you have something like a 100 nanosecond time error requirement, where did that come from? What was it really just you kind of picked a number and sort of settled on that, or did it come from some of your AI analysis? And in general, kind of like the preceding thing, try to get into data as much as possible and kind of actually get to the details of these questions and actually show the benefit with real data running in a real system was kind of the idea. And the general kind of thinking is this is sort of the way forward, at least for AI, to kind of like try to make the thing clear. So with that, kind of the action items that we sort of came out of the meeting with was that, like Dan presented, and when the whole thing started, is we need to look through those projects that TSA IIW has and try to create more projects and try to create more work to do this sort of thing. That's going to be kind of a future area of focus. Again, mostly for AI. OCP TAP covers a lot of topics, obviously, and so this isn't the only thing. But for the AI topic, that's kind of the idea. And I'll give a plug for a presentation that Meta is going to do next week at the same time, this time slot and everything, on time sync to avoid congestion. Med can correct me if I'm wrong, but I think this initial presentation next week is going to focus on kind of more of the state of the art, like basically what are people doing for AI workloads today? What kind of protocols, how do those protocols work? Things like that. And then we may have a follow-on presentation to get more into, what could we do, and what could we actually try to emulate or experiment with or whatever. And to me, I'm really looking forward to that. That's going to be, I think, kind of a good kickoff to the whole sort of idea. And so with that, that's all I had. And so now that I've kind of done rambling, anybody have any questions, comments?
Well, thanks, Rodney, for presenting all that. Just to confirm what you just said, yes. So the plan is to have 2 presentations, and this was a great discussion that happened in OCP. And I think the focus, it's great to kind of look at a lot of the presentations and the work being done to increase accuracy, etc. But I think the takeaway that a whole bunch of us wanted to take from that was we know, for example, that we can distribute time sync to servers and to application level to say 1 nanosecond. So how about we flip the problem and then say, assume that we can do this everywhere in the data center. We have a nanosecond accuracy. What can we do with it? So part of the presentation, this is basically, let's take one example. So we know, for example, that congestion control, and avoidance, so basically scheduling traffic or shaping traffic, uses delays. But these delays are very coarse at the microsecond. So the goal of the exercise for this was to basically say, okay, let's assume we have this and we have it reliable. How can precise timing affect these things? So the first part would be like, okay, here is how congestion has been dealt with over the last bit, and what's the active research area right now, and of course, focusing on AI and that one. And it would be great if other people also look at other applications. This is one thing that came out of it that I had interest in it and could help contribute. It would be great if other people could actually also take the baton and look for other applications and other, but kind of within the same framework. So basically, okay, we have precise timing. We could assume that. How could it better applications in various aspects of data center, edge data center, whatever other applications.
Another
I
one.
totally
Sorry,
agree.
someone else go ahead.
Yeah, go ahead. Yeah,
No,
sure.
I was going to say a similar area that's related to AI, but on the flip side is I think, at least I wasn't on some of these prior calls, but my vague understanding this is really how do we time sync accurately our AI accelerators. But one of the areas I've seen this in finance, and it applies to other industries as well, where it's extraordinarily important to have precise time, is more for your input data you're feeding into artificial intelligence. And do you know exactly to the nanosecond when a particular event happened? And you see this, definitely in financial systems, automated data, but a lot of other things like cybersecurity. Can I accurately monitor a data center and every packet and every event and every decision being made going throughout these very complex devices? And can I detect anomalies? My ability to detect anomalies is to what extent do I have any idea what the sequence of events are? And it's synchronized very precisely. We're running this stuff at 400 gigabit Ethernet, and so plus or minus, even 50 nanos. Well, now the order of packets is switching, and so it makes it fun. But I think this could be an area more and more of just, one, what are all the different data sources we're feeding into AI that would benefit from enormously better time sinks? But then also just monitoring data centers from a cybersecurity perspective, and just causation, and not even cybersecurity, just this is just a complex machine. How do we instrument it and understand it? But our ability to do that is the quality of our measurements and data points.
Right.
Something I like to add here is this is also similar, perhaps, of a problem for quantum computing, and how quantum computing will basically find its place. See, I was trying to explain this to a less familiar person in this field, and I came across, and people who know me closely know I love analogies. So you look at mathematics, right? Like, for example, in mathematics, you have, let's say, natural numbers, and you add zero, and then it becomes like, I don't know, it keeps adding things and so on, and you go like, I don't know, fractions and blah blah blah, and then you have like, oh God, like we need root square of negatives. And at that point, you introduce complex numbers. You don't use complex numbers for day-to-day things. You don't use complex numbers for addressing. You don't use complex for so many things, right? But complex numbers will have their own things when they want to describe phasors and like so many other things all of a sudden show up for complex numbers. And on the faceplate, they might not show. They just show like, oh, okay, they're going to solve, for example, this, right? And if for those who are not aware of, let's say, complex numbers, you go to the era before complex numbers were introduced, they're like, okay, there is no, let's say, answer for negative root square, similar to divide by zero and blah, blah, and all of this. So when precise time comes in, you basically have a set of problems that, or maybe before I get to precise time, like with quantum computer, you're going through the algorithms that they deal with, let's say, Turing machine. There is an instruction, there is data, you process, you go through. But then the moment you want to have, as you make a decision, you want to consider a lot of other parameters in the same time, concurrently. That is where your Turing machine will really fall apart, or you will accept some crazy, unrealizable complexity. And at that point, you're like, wow, I need like these properties, like, I don't know, entanglement and superposition and, like all these interference and yeah, I don't have those. And I'm trying to put them in, a numeric Turing machine, and then Turing machine will suffer so much because there's so many interactions. You basically got a halting time, and you do all these processes and you go further, and then halt time and do this, and it would just go, like the complexity would just go crazy. So that is where a complex number gets introduced. Like, here's a quantum computer with qubits, and you can solve this, blah, blah, blah. So I think there is something there in between as well, where even if you have qubits, you need to, let's say, go from normal computation, classical computing to, let's say, these kind of problems. And these problems are not off there, when we're trying to solve like, Lorentz weather or something. No, they actually come very close to most of the things we do. Even in AI, when we do optimization, we need to consider a lot of things, not take like, for example, there's an algorithm recently I've been working with that basically tries to find pairs and these pairs are not replenished, and it tries to stack pairs as it goes through, is not like, let's say, a numeric that you put them all in one direction. As it goes through the algorithm, it starves options because the good options get picked in the beginning, and in the end it will be like, sorry, that's all what we got, and it has to basically plummet. While if you want to really solve it properly, you don't need to necessarily take the best, you take good answers, and then you consider everything together. I mean, again, analogy is like you go to a potluck, there's dishes of everyone brought in, and they're not that many, and then you're first in line and you're like, wow, I like that dish so much, I'm gonna scoop it all. Then you look back, you're like, uh-oh, there are all these kids there, they might love this, maybe I will go easy on this. And you're not gonna take an optimal match because you consider the whole, right? So to get to those kind of problems, now we are looking for a root square of negative, basically something that normal computers cannot do. You look for these alternatives, and what time brings in is, like always I say, like this pseudo entanglement is now without the need of, let's say, exchanges of like handshakes. You can have schedules that they can give you, let's say, concurrency. It's like, again, this is also a pseudo concurrency, because I mean, if you listen to Paul's talk last week, you see most of these things are illusions, really illusions, and we're trying to use these illusions for, I mean, they're illusions with good statistics, and we want to use those to take advantage of them, like avoid, like, let's say, multiple handshakes. It will be like factorials, like a lot of these things end up with n factorials. So I hope I gave you more questions than answers. I will.
Well, no, I mean, see if this sounds right. I would maybe combine, see if this sounds correct. I would kind of combine maybe what you said with what Med said, in the sense that, let's say that we posit as a base assumption, assume that every computing unit in your data center, CPU, GPU, quantum computing device, and so on, has 1 nanosecond of synchronization. And of course, people will say, oh, well, that's going to cost too much money, or it's going to be too hard. But we kind of say, well, no, but we timing experts actually think that's not that hard. So can we just assume that, then I think you're right. Like, the next level of questions you're going to get is, well, for distributed databases, for example, I only need a microsecond. I don't need a nanosecond. So, and I have this other application and this other and this other. So maybe 90-something% of what I'm doing, I don't need a nanosecond, and I've heard that from a lot of people, and it's a reasonable thing to say. But by getting that 1 nanosecond, kind of like a qubit, that a lot of people say, well, I don't need quantum computing. I can do fine without it. Same kind of thing. It's like, well, but if you open your sort of like set of experimentation to actually consider, well, what could I do if I had 1 nanosecond? Like, could I actually offset the compute of my different GPUs, even on a single board, to be more power efficient? Or could I do something, with that level of kind of fine-grained timing, and then we experiment with it? Again, back to the previous slide, we show it, we prove it, because a lot of us work with companies where we can even prototype hardware things, and it seems like that kind of opens up the window of open-mindedness, let's say. That, like, okay, maybe I don't need this 1 nanosecond for everything, and we would say, no, that's totally fine. We realize you don't need it for everything, but assume you have it,
Rodney, one thing I add before I give the floor to the others is, by those analogies, what I try to basically reinforce is, it's fine if you have problems that they don't need it. And
right.
that is basically what I was trying to, convey, like, during the roundtable, and probably sounded a little bit negative, is it's fine. There are problems that, I mean, there's a lot, it's the same way what I said in the beginning. Yeah, you have, like, I don't know, rational numbers, you have like fraction numbers, all of it.
Right.
They don't need complex numbers. You need complex number for a subset of, let's say, equations that they go crazy, and then you have to solve them differently. So if you go with that mindset, I think it will make it very clear. But when you have someone going on stage that is a vendor that is focused on the how, not why,
Right.
claims, like all these crazy things, then you're setting the wrong expectations. And then people will oh, I'm not going to use it. I just need
Right.
I need that. And, blah, 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 blah. And then you all of a sudden have all the valuable things also underseen. So I think it's very important to at some point pause and say like, okay, and that's why I took my focus off. I took my foot from the pedal. I'm like, let's go with the inertia. Let's see how far it goes. And I even made the exercise. Hey, if I want to kill this project, who's going to complain? And then, and then I saw like, oh, no, we need it. Okay, great. So great. I hear that, so take your foot off the pedal and see, like, do you have inertia, or you're in a virtual reality that you're gonna, the moment you take your pedal off, you're like, cook, stop.
Right.
No, that's all I mean.
No, and I totally agree. I mean, maybe to put it another way, that if we go through kind of like different exercises and we show that precise time sync doesn't benefit AI, that's okay too, right?
Yeah,
Right? I mean, there's nothing wrong with that. That's not a failure or anything like that. It's just like, oh well, we went through all these exercises and experiments and trying different things, and the math didn't work out. That's okay. Yeah. I've seen that time and time again with PTP in particular.
So I've got maybe a unique view because of what I do here at OCP and my familiarity with, time-sensitive networking and so on. What I will do is suggest that there's very practical uses for high precision timing. And, one of them is, and they start from very simple and they get very specific. But if you look at very simple problems that we have that are outstanding, that are not solved, one of them is heterogeneous computing, right? So you have maybe processors of different classes and different speeds and things like that. And so you have to have, the greatest common denominator in timing, right? In synchronization. So whatever the most precise instrument that you have or component that you have, you need to match that timing everywhere. We have kind of a pattern for this in other areas too. Just thought of this one too, but doing DSPs, when I was doing DSPs, you would have systems that had a primary frequency, and then you would basically upscale those frequencies or downscale those frequencies to match whatever problem that you were solving. And I think that's probably the right approach for synchronization. Like if you go with ultra high precise, synchronization, then as long as everything is a multiple of that, then you can step down, right? And you can have the slower timing, but you could be assured that the accuracy is still, within our tolerance. And so the other wonderful thing and the perspective I was going to tell you is that, here at OCP, we have the ability to kind of set these requirements, right? So, we can drive this and we can say, hey, a data center should have sources that are, available that meet this requirement, right? And it could be very high, very precise, but it doesn't mean that every device within that, domain operates at that same level of precision. So
Right.
I'll stop there.
No, that makes a lot of sense. All right. Anybody else?
Just following up on this other point about the distributed database guys, they only need a microsecond. I strongly push back against that. I think originally
I kind of
this was a legacy, just intuitively, and especially if you start getting these machines that have thousands of cores, where you could have, literally a dozen plus 400 gig Ethernet NICs going into one box, and you only care to a microsecond. I call bullshit.
Right.
I mean,
yeah, David, where they bring up. Yeah, I'm pretty sure. I'm just trying to clarify for the others. They bring this up is from the Cal theory.
yeah.
And basically, it's the race between latency and the clock accurate. I'm not schooling you. You know that. I'm just clarifying for like the others.
But I think a lot of this is just
because of latency. Yeah, because the latency is going down with
latency is going down, measurement accuracy goes up, everything else goes up.
There's high expectation from the clock.
Yeah. And that's where sometimes, I mean, not to sound like a dick, but I'd be skeptical of when experts in a particular niche say, I don't need that. It's more that they're dealing with 30 years of legacy of what was the technology
Right,
of
right.
everything at that point, and that sort of constrained everything. And then it's like, it's like, well, I don't need a petabyte of RAM for my, distributed database. Yes, I do. Give me a petabyte of RAM. I will find a way to use it, as long as it's not exorbitantly expensive. But we tend to engineer systems around the ecosystem we have. And that's where I think exercises like this are very useful, to be very precise and thorough about why did we as an industry or as experts make these decisions, these architectures, these specs exactly when we did. And then what are the relative sensitivities of all the knobs? And those knobs are not being turned at the same rate. Some are changing 5% a year, some are changing 300%. And we don't, and it's just, as humans, we're not capable of fully looking back at our own biases of why do we say this is the way we do things. It's like, well, that's the way we always did it, and we just
David, that's
incrementally made
also
it a little better.
I mean, I'm not trying to correct you. It's just like
feel free. You can tell me I'm wrong.
I'm elaborating. Like part of it is you're working with human. You're not working with system robots or something. So the human aspect is very important.
Yes.
I mean, seriously, like when I entered like the professional world of job, again, whatever is getting recorded, I don't care. I'm not saying anything appropriate. I figured out that my people skills are actually more important often than my technical skills. And I saw so many, let's say, good ideas
Well, you need to take it off your desktop.
Get shut down only because, let's say, those who had those ideas were not able to navigate the human aspect of things. There was like a previous company I was working, they had the leading technology that was basically going to alleviate, like the work that some technicians have to do. Basically, 2 weeks work of technicians, tedious work of technicians that was proven to be very subjective to the technician that does the scoring, ended up basically being resolved with a machine learning technique that was doing the whole thing in 30 seconds. But unfortunately, there was the human aspect that, let's say, those technicians lobbied with the doctors because they didn't want to lose their jobs. And that project never took off, while that project was actually a valuable thing. So there is this part as well. So that's why it's also very important how you make this, like the, like, what do you call the ramping smooth and make it more of a win-win solution rather than like, okay, there will be a lot of people that they will lose, like, their jobs because they're thinking without, consideration of precise time, and bam, we have this thing there, you're obsolete, like instead you have to think how we can ramp it up that you also ally those people. It is a reality. It sucks. It is a reality. We deal with human.
100% agree.
Yeah. And David, I do agree. I guess sometimes when I hear the numbers, like, well, I need this number and that number, I guess sort of comparing to some of my experience, like for some of the other applications that have used PTP, like say industrial automation, which has been using PTP since the first standard in 2002, over 20 years.
Yep.
When folks in that community say like, I need 1 microsecond of timing error, which is, for example, one of the numbers that's in their IEEE standard, the 6802 thing. If you ask that crowd, where did that 1 microsecond come from? They can produce huge amounts of data and analysis and simulation and experience with deployments over the last couple of decades. And, in other words, they can answer that question of why 1 microsecond really, really well.
Like and for physical systems,
show you, because it's like, here's a physical system that we have in an actual factory that had 100 nodes, and we needed 1 microsecond for this reason, for the robots that were doing this and that.
Exactly.
And there's all this like data they can throw at you to show this is where that number comes from. It wasn't just off the top of somebody's head. Like it was like,
as soon as you deal with 3D real world physical systems, I 100% agree. Because then it's much more, you're bound by actual physics.
You're bound by physics, right? Yeah.
When you get into our world, it's just really as clocks, core counts, everything else keeps going up. They're going up at rates dramatically faster than the rate at which we're suddenly allowed to go above the speed.
You're right. That's true. And you're right. And automotive is another example that, they can come up with really hard real numbers because a car is taking inputs and processing them and doing outputs, essentially, and it's all real world stuff. And it's easy for them, to say, well, here's the reason why I have this number. Yeah,
exactly.
Yeah, you're right. It's more challenging for data centers because.
Yeah, but we try to act that way. Like it is a
we try
system.
to,
It's
or
like,
we try
no,
to
it's
apply
really
that
not.
assumption.
Yep.
Yeah.
Or the other way you could look at it too is, okay, then you hire some of those people, you bring them to Elon Musk, and you say, okay, now we're going to do the same thing, but at like 20,000 miles an hour, right?
Right.
Does that 1 microsecond still hold? Wait, no, wait a minute, this changes all of the math.
Right.
Suddenly it gets a lot more important.
Right, exactly.
Mach 5 or whatever it is they do.
Bijan,
Yeah, I worked on satellite corrections a long time ago in my career with GPS, right? And the problem is now is not now.
Right.
So anyway.
Absolutely.
Sorry, Ahmad, did you need something? Were you saying something?
no, I was giving you the floor.
Oh, okay, yeah.
Okay.
Yeah, no, so now is not now. So our fudge factor is to become more precise in our timing, and that way we can have more precise sensing and more precise feedback, deterministic feedback and that kind of thing. So pseudo-deterministic.
All right. Anybody got anything else?
I have a question, Rodney. You mentioned
Sure.
a very good comment that we need to get more data to justify whatever we want to do. So for this particular project, as you know, Dan has been trying, and I worked with him to get this data by getting studios, blah, blah, blah. You know the story.
Right.
So now, given that we have a meeting with everybody, how we can get this data?
You give me the hardware, I can get students to generate the data. And I've done other things like this on micro scales, more for the high frequency side, or just
Really?
doing like GPU total cost of ownership. But the issue is just what sort of scale do we need that other people are interested? Because sometimes there's something that you can do with 6 or 8 machines in a rack, but that doesn't
Right.
scale to anything that anyone at the the C-suite cares about.
And Hisham, I would say it's a little soon to say, but I think one of the things Med and I have talked about a little bit offline, and Med, correct me if I'm saying something wrong, is so there's different ways to try to experiment. One is to get an actual data center, with actual stuff, and then do some experimentation there. That might be an option. Like David said, if we can get the hardware, we can do a lot with that. One step maybe kind of below that might be emulation, meaning, in other words, get some network emulation hardware, which my company happens to make, and so you're not running in an actual data center, but you're running over real Ethernet, with real emulations of, say, 1 million nodes or something like that, but it's emulated. So it's hardware, it's a real network, but it's emulated. That might be one step down that, at least to me, I think I might be able to help in the sense that I work for a company that's got some emulation equipment and stuff. So there's different options and different ways we could try to do it. I don't know, Med, did you have any thoughts on that, or?
Yeah, I think you put a good summary to it. So I think initially when we discussed this offline, we're trying to come up with something, if the idea has legs, and then we can basically prototype it, have someone, a student, do some work on it. What would be the easiest first step before? So emulation was a great kind of stepping stone towards, because kind of doing something, a deployment at scale, even something what David is mentioning, would be very, very useful, especially if the solution requires some amount of hardware. So something like a smart NIC with some hardware assist. At some point, if you want to do precise timing and kind of do any real data from the emulation will get you a step, but then at some point doing it at kind of a controlled test environment would be definitely the next step before anyone would want to basically put it on even a lab deployment at a data center scale, which is quite actually.
So sometimes
agree.
Go ahead.
Oh, sometimes what
go
I've
ahead.
seen in other industries is you actually get together with industry participants. And right now, at least from what I've seen in presentations like this, it's very high level. We want to do AI at some scale of some on some hardware. Can we get dramatically more precise? Like, okay, what is our input data set? How many neural nets are we training? What are we running this on? And then once you have all of that, you start building out the infrastructure of how do I make this turnkey for different industry participants, whether it's vendors or hyperscalers or some of the big tech that are just trying to control this entire ecosystem, where they can take verbatim that and run it on their different scales and get us the raw data that we then use to tune and basically create the probability distributions for the emulator. But you really
absolutely
need that
very
precise data, because otherwise, like, I don't know, like, are we pulling in a terabyte at a time?
Right.
The same 1 terabyte going to 5,000 nodes, or does each one see a different node? What are the access times? What are the memory and storage configs? And getting all of that data, or at least understanding all of the variables. I think it was like step 0 before we can even simulate, because that's the thing that I'm always curious about that I don't have the data for yet. Like, okay, I know what LLMs are. I know how to do, neural nets to detect dogs versus cats, but numbers we're dealing with, resolutions, data sizes, scale, etc. And then you sort of take it from there. But that's your kernel, I think, that you can grow out of.
Absolutely agree. Anybody else? We're running a little close to the end. All right. Well, thanks everybody. Great discussion. This is definitely what I was hoping for, and totally agree.
Maybe we need one more session for more discussions, Rod.
I mean, to be honest, I'm hopeful of meds next week. It might be.
Okay.
I mean, because of the kind of things that David was describing. I think meds, I'm hoping next week is kind of the first step in that direction, that we start getting like real. Like, what are we talking about, and what are we going to actually try to do? And the first step in that is just simply understanding what's done today, and that's got to be the first step, and then from there you go, well, we could try this, we could try that. And
you're right. So
I kind of look at meds as the next step to be, and maybe I'm putting too much pressure on med, but
the other thing is, I'd like to add, Rodney, is that if there's other people that kind of feel strongly about a specific application, that would be great as well. So I think this is one avenue that kind of, we know that delays and timing has been used in congestion and definitely into shaping and scheduling traffic. So how could precise make it better? But there's a ton of other stuff. So if there is people in the call that actually feel about this and want to also jump in and kind of take it the next step, that would be great as well.
Absolutely. Yep.
So maybe, Rod and Med, distributed machine learning will be another application.
Sure. Yeah.
But again,
I think machine learning these days is often distributed.
You're right.
Yeah.
I saw a great use case that was presented. I've read a paper or two and it's been presented, but I haven't really seen any follow-up. It might be worth it. And that's that, any kind of load store component is kind of idling when it's doing one thing or the other, right? So the idea was, if you had very precise time, that you could have these very controllable sleep cycles or something like that, that you can reduce a lot of idle power from the data center, for example. So everybody would have to be on the same tick, be able to pull that off.
To do that kind of thing. Yeah, that's true.
All right, it looks like next week we're going to have all the problems of timing solved in the world. Med, no pressure.
It's part one, what everybody else did.
with us helping you, of course.
Yes, of course.
let the why guys sorry, let the how guys go on stage and claim for it then. All right.
All right. Well,
We'll see
thanks
everyone
everyone.
next
Yeah.
week then.
All
Thanks,
right.
everyone.
Thanks.
Thank you
Thank
very
you,
much.
everyone.
Good session.
Bye.
Thank you. Bye.